Now, as I said, we start with the common emitter configuration. Common emitter configuration. And in the common emitter configuration, there can be, there are some sub configurations. We look at the first one that we term as single power rail, double emitter resistor, common emitter amplifier. Single power rail means there's only one DC power source in here. So we've got VCC, and here I'm now explaining what's going on in the notes. Okay, so we've got the power source called VCC, and it's a single one because it's single power rail. We've got RC that side, RB1 on this side, we have RB2 on this side, we have our transistor NPN, for example, and then we've got double emitter. Simply means there are two emitter resistors, RE1 as well as RE2, all of them connected to ground because it's a single power supply, just a VCC to ground power supply, one single power rail. Okay, and we have one of the emitters being bypassed by capacitor that we can call CE, or emitter capacitor. The input is coming through the circuit to the circuit through the base, so that's the input side, and here we've got a capacitor CI, or input capacitor. Then that's where the input AC voltage is applied, and this input voltage comes from a source AC voltage Vs through a source resistance Rs. So Vs is applied to the amplifier, but part of it get consumed by Rs. So Vs is basically splitted between V across Rs, which is the voltage drop across the source resistance, and Vi. And we're gonna see how they are related. Vi is related to Vs because at the end of the day, what get amplified is Vi. Okay. Then the output is taken on the collector side, and it goes through an output capacitor, and to generate V out. And V out is applied through to a load, RL. So remember, we amplify a circuit, but it gets loaded. The amplified version is sometimes applied to a load. For example, in the case of sound, microphone will be Vs, wire will introduce Rs. We get Vi at the end of the day, which is a reduced Vs because some of it will have been consumed by Rs. That get amplified through the amplifier circuit, and then we get an output amplified voltage which get applied on a load, which in this case can be a speaker, for instance. So a speaker with a certain resistance RL. So we will look at three things in solving most of problems. We're gonna do the DC analysis, we're gonna do the AC analysis, and we will look at the loading effect. Loading effect has to do with what is the influence of having RL and not having it on the gain of the amplifier. What is the influence of having RS and not having RS on the gain of the amplifier? And as we do all of this, our ultimate objective will be to characterize the amplifier, meaning to understand this specific amplifier is designed with this BJT. If used in these circumstances, will give you the following gain, because of course characterizing an amplifier means you need to know, you're interested in knowing how much gain you can get out of it. We're going to look at what we call input impedance, and we're going to look at what we call output impedance, because take note that the characteristics of an ideal amplifier meaning the amplifier that one would like to have is the one with a very high gain, because no one would want less gain. You can have very high gain, then you can always tune it lower, but you must be able to have high gain. Input impedance ideally is very high, and you'll notice why. And the output impedance ideal one will be low. You also notice why. But we're going to analyze in terms of those three parameters. We're going to look at the loading effect, and the steps will be DC analysis, AC analysis, then loading effect. So let's start. In terms of DC analysis, although this has been discussed in electronics 1 as well as in this electronics 2, the first thing we do is to see what does the circuit become when we do DC analysis. The circuit, we know that in DC capacitors we have like open circuits, so that reduces the circuit to the following: RB1, RB2, RE1 is still there, RC is there. Now at the base, because the capacitor behaves like an open circuit, so the rest of the circuit is cut out. You agree? The rest of the circuit after the base is cut out. At the collector there was also a capacitor, so it behaves like an open circuit, so the rest of that part is cut out DC analysis wise, because of course we are on step 1, which is DC analysis, where capacitors behave like open circuits. Okay, now the capacitor on RE2 will also behave like an open circuit, which means it's gonna be an open circuit there. So it's more like RE is present and there's nothing there. So you can as much remove that, because CE is behaving like an open circuit, means it's infinity. So if you think about, the resistance, its resistance is infinity. So it's more like infinity in parallel of something, which gives that something, which is RE in this case. So that's what we end up with. Why is it RE? Because you can work it out. 1 over infinity plus 1 over RE to the power minus 1. If you want to prove it mathematically, so that will be 0 plus 1 over RE to the power minus 1, which will give RE. So anything in parallel with open circuit gives the resistor considered here. So at the end of the day, we've got two emitter resistors, RE1 and RE2, in series, which can be replaced by a single one, which is the sum of the two. RC, we have a single one, which happens to be the sum of both. RB2 and ground. So that's what's left of the circuit DC analysis wise. So we can start with the DC analysis itself, and it's gonna go as follows. DC analysis. So now I have to redraw the circuit. RB1, RB2, VCC, RC, the transistor is there, a single RE, which is RE1 plus RE2, and ground. So to do the DC analysis, what is the main point of interest? So the question is normally guiding, and we ask you for IC, IB, IE, V, voltage drop across RC, voltage at the collector, and so on. But we know that the link at the end of it, ultimately, because the input is AC, we want to do AC analysis and see how the input voltage applied gets amplified, meaning its gain, the input impedance of the amplifier, the output impedance. So, and we know that the DC component that makes the link between AC analysis and DC analysis is IC. So collector current happens then to be the most important DC analysis aspect to get right. So you must make sure you get IC right, otherwise your AC analysis suffers. So as we've mentioned, through Thevenin and Norton conversion, this circuit can be further changed into a single VB, actually VBB, sorry, going through a resistor RBB, which, as explained earlier on is in the previous videos, is RB1 in parallel with RB2, and through the transistor single RE, which is the sum of the two, plus RE2 the way to ground. Then we still have RC, and we've got VCC. The analysis of this circuit, and IB flowing here, of course. The analysis of this circuit, this is one alternative. I showed you the other alternative, which results in 3 simultaneous equations that you solve with the objective of getting IB. Why is IB important? Because once you've got IB, IC is just beta times IB, and the rest of, then you can work out IE as well as IC plus IB, and you can get most of the voltages, and your DC analysis becomes easier. So IC is still flowing there, and IE is flowing here. So now, the analysis of such a circuit lies on two pieces of interest. The one is this loop here, and the other one is that loop. So here in that voltage loop, of course, you apply Kirchhoff's voltage law. You're also going to apply Kirchhoff's voltage law in that loop. So to apply VBB, how is it computed, by the way? As you mentioned it earlier in the previous video, VBB is computed as VCC times RB by voltage divider, basically RB2 over RB1 plus RB2. So if you apply Kirchhoff's voltage law in that loop, VBB is computed above, must be equal to RBB times the current that flows through it, which is IB, plus the VBE drop, voltage drop, which is 0.7 for silicon, 0.3 for germanium, but we focus on silicon, so that will be VBE, which is 0.7, plus RE multiplied by IE, which is the voltage drop across the emitter resistor. Knowing that IE is IB times beta plus 1, that leads to VBB that we will have computed by voltage divider, reminder. RBB will be equal to RBB IB plus 0.7 plus RE times beta plus 1, beta being known or given or derived, but given most of times. We can work out IB quite easily as VBB minus VBE, which is 0.7, divided by RBB plus RE times beta plus 1. As I said, from there we can work out IC, which is nothing but IB times beta, and you can also work out IE, which is IB plus IC. If you look at the other Kirchhoff's voltage loop all the way from VCC to ground, that will allow you to get another very important DC characteristic of a transistor, which is VCE, collector to emitter voltage, which can come from the fact that VCC in that loop must be equal to RC IC, because that's the current that flows through it. Then you go through from the collector to emitter, and you go all the way to adding RE times IE. Then you can extract VCE from here as being equal to VCC minus RC IC minus RE IE. VCE is very important because it helps in calculating, as learned in electronics 1, the power dissipated in the transistor, which is nothing but VCE times IC. And it defines the quiescent points in the active region under which you are operating the transistor, which is defined by ICQ, which is IC, and VCE quiescent, which is VCE. Why is it important to know the power dissipated in the transistor? Because a transistor has got a maximum power that can be dissipated in it, that you find in its datasheet normally, PD max, which is also sometimes called the rating power. Rating power, meaning the maximum power it can dissipate before it burns. And you must always operate the transistor at a point Q, meaning at a certain IC, Q, and VCE, IC and VCE, in such a way that PD, which is VC times IC, is always less, maintained to be less than the rating or the maximum power. That's very important. But that will conclude the DC analysis basically. And one can safely move towards AC analysis. Now, in terms of AC analysis, and we're doing this in hybrid pi model as discussed. And in hybrid pi model, there are a couple of rules. Capacitors become short circuits. Caps become short circuits. So we go to the original circuit in which capacitor becomes short circuits. We've got an AC supply. That's one rule. The other one is that voltage sources like VCC, DC voltage sources, DC ones basically. That the AC one, DC ones become ground basically. So as you go from VS, you go through RS. AC voltage sources such as RS, you know the difference between an AC voltage source. We normally use that symbol to say it's AC. For DC, we often use the battery symbol. Okay, very important. So these become ground, but these ones are there, the AC sources. So VS remains. The cap is now, CI is now a short circuit. So that would have been CI basically. It behaves like a short circuit. That would reconnect the rest of the packet of the circuit which was cut in the DC analysis back to the circuit. We've got RB1 and RB2. By the fact that we've got ground there, VCC becomes ground. That makes RB1 and RB2 become in parallel now in reality. So at the end of the day, you've got now RB1 in parallel of RB2 instead of them being like in series as they were in the original circuit. Then you enter the transistor and you just deposit, or you just replace the small signal AC equivalent circuit of the transistor, depending on whether it's an NPN or PNP. So in our case, it's an NPN. So as we go from the base, we know that in an NPN, when we've done this many times, you've got IB flowing, you've got R pi, you've got plus minus VBE there. You have current source, it's NPN, so IB is coming in, IC is flowing down. That's where your collector is, IC is flowing that way. They meet at the emitter to form IE, and IE, we are now at the emitter. So that will have replaced the transistor, because that is AC equivalent circuit or small signal equivalent circuit. Now we connect each part of the circuit to each terminal of the transistor. On the collector side, to start with that, we've got RC going to VCC, which has become now ground, because VCC is a DC voltage source which has become ground. So basically we now have RC going to ground. And we also have a path that leads through CO, which has become a short circuit. And it's leading towards RL. We reach V out, sorry. And we go through RL all the way to ground. So that concludes the collector side. On the emitter side, CE becomes a short circuit. But before CE, we go through RE1 first. When we reach that point where RE2 is, we have RE2 to ground, but CE, which has become a short circuit in AC, all the way to ground. Now you got 0 ohm in parallel with RE2. 0 ohm in parallel with anything gives 0 ohms. So at the end of the day, it's more like you are going straight to ground through a 0 ohm. So that's how RE2 doesn't get to participate or to take part in the AC analysis of this specific type, where one of the two emitters, because it's double emitter case, is bypassed by capacitor CE. And this circuit that you obtain at the end with minor tweaks that I'll show you now is becoming what we call the small signal AC equivalent circuit of the amplifier, BJT amplifier circuit. So that the AC equivalent circuit of the small signal AC equivalent circuit of the amplifier circuit. So this point is grounded basically because RE2 is in parallel with 0 ohm. But what do you need to complete this? You need to identify the three characteristics of an amplifier. Obviously, IC is also, as we computed it before, GMV pi. But you need to identify where is the input VI, because we know VS drops a bit before it becomes VI. VI is always the actual signal that at the end of the day gets amplified. And it's a piece of VS. Vout, of course, is the output voltage in this case because it's common emitter. You're observing from the emitter and it's on the collector. Now, to simplify this model, we present what we call the hybrid pi model, and sometimes we ask you guys to calculate to draw this of the entire amplifier, entire BJT amplifier. So this one is a more simplistic or simplified model where you've got VS, you've got RS, and we know that VS gets shared between RS and some more common or a summary type of input resistance of the amplifier. So this comes in when we look at the whole amplifier as that box, and we have as that box, and we've got the source applied to it through a source resistance, and we've got the load on the other side. So there must be some input resistance or impedance. So sometimes we call it Rin as well, resistance in this case. Impedance will make much more sense when we start considering caps in electronics, but for now, impedance and resistance is all acceptable. Zin, there must be some input resistance, and what we know is that we end up with a bigger, so VI is there, sharing VS, which is a piece of VS. It's the piece of VS applied on Zin, some input resistance Rin or Zin, which means, going back to small signal analysis to complete it, that is, if you look at from that point inward in the amplifier, that's what you've got, that's what we call your input impedance, or Zin, also sometimes called Rin, the same thing. And when you look at this point before, so we normally put discontinuous line, sorry. If you look inside the amplifier from that point, on the looking from the output side, you've got what we call Z out, or output impedance, also called R out. So at the end of the day, you also get V out there. So as you move from VI to V out is actually part of a voltage. So you get a certain gain that we call AVO, or open loop gain, multiplied by VI. So that's what you get on the output side. And here, this match voltage, which is the VI multiplied by the gain, meaning by how much it has been boosted, is shared once more between Z out, and that way your V out is your actual V out that ends up on the load is, and RL. So this is the hybrid pi model of the BJT amplifier as a whole, but this is the small signal equivalent circuit, which is more detailed, right? Okay.